Hello students, welcome to the next lecture on conventional manufacturing processes, and in this lecture we will discuss about different drilling tool holding devices and one numerical on machining time calculation for drilling operations. So first of all, as the name suggests, tool holding devices means the devices used to hold the drilling tool. And the most widely used tool holding devices are drill chuck, drill sleeve, socket, and the drill drift. Here, drill drift is not the tool holding devices, but many of times used to remove the chuck or maybe sleeve or the socket after the operation gets completed. So let us start with the first one, that is the drill chuck. Now, as you can see over here, this one is the drill chuck. Just a second. Okay, so this one is the drill chuck, and as you can see over here, these are the holding chuck, and these are nothing but the three jaw chucks. Then this is the outer ring, and this one is the key which is used to expand the jaws and to fix the jaws after when the component gets fixed inside these jaws. So this drill chuck is most popular drill bit holding devices in the world. And when the person is working with the shank type drill bits, at that time this drill chuck is used. And it is mostly used in all types of the industrial devices during the drilling operations. Now, to use this drill chuck, one must need to fit this drill chuck inside the spindle of the drilling machine. And mainly, as I have discussed, there are main three components of the drill chuck, and they are: first one is the jaw, second is the nut ring, and third one is the key, which is used to fix the jaws when the component gets fixed. And these most of the drill chucks have the three jaws, but some of them also have the four jaws. And mostly three jaw chuck are used by many of the peoples. And these jaws have inbuilt teeth inside them that strengthen their grip over the drill bit that is used. Now the next one, that is the drill sleeve. As you can see over here, this one is the drill sleeve. And this drill sleeve is used when one is working with the taper shank drill bits. And by using this sleeve, one can hold drill bits whose size is equal to the taper size of the spindle. And this is most commonly used during the radial drill machine. So radial drill machine gets its application when holding the workpieces when holding the drill tool using the drilling sleeve. And it has a standard taper hole inside the drill sleeve. So one must need to fit the taper shank drill bit in this hole and then fit the sleeve into the spindle. So this is how this drill sleeve is used to hold the drill bit. Now the next one, that is the socket. And when the person is working with the taper shank drill bit whose taper size is larger than the taper size of the spindle, at that time this socket type holding device is used. So the application of all these three holding devices are different, and based on the requirement one should use maybe a drill chuck, drill sleeve, or the drill socket. So these are the work holding devices used during the application of drilling machines. Now we will discuss about one example to calculate the machining time for the drilling operation. So the data is given over here, and as you can see, to solve any of the example, first one must need to write all the given data and then focus on what they have asked from the example. So here, as you can see, what they have asked is, they have asked us to determine the time required to drill hole. That means our first and foremost requirement is what is to calculate the drilling time, and we know that the equation for drilling time that is L divided by F, and here L is the overall distance traveled by the drill bit, F indicates the feed, and N indicates the revolution per minute. So now, as the example suggests, now one need to find the time required to drill a hole. The diameter is 25 mm. So D that is the 25 mm. And in cast iron workpiece of 50 mm thick using a high speed steel drill. So the depth that we need to machine, that is the 50 mm. So thickness, that is 50 mm. So the length traveled by the drilling tool on the workpiece, that is the L or T. You can indicate it as the L or maybe the thickness. Now the cutting speed and feed rate for the operation may be assumed to be 0.50 meter per second and 0.5 mm per revolution. That means the cutting speed given as 0.50 meter per second and the feed rate is given as 0.5 mm per revolution. Here the drill point angle is 118 degree and approach and over travel may be assumed to be 8 mm. So what is this approach and over travel? So as we can see, suppose if in a component we need to drill a hole up to the thickness T. Now when the drill bit is touching the workpiece, at this time it is not directly removing the material, but when this much of portion gets inside the workpiece, then and then only machining takes place. So this distance is nothing but the approach distance, which is indicated as the AP. Similarly, when the entirely drill bit gets outside, then and then only we are getting the desired hole. That means drill needs to travel extra this much of distance, and this distance is nothing but the over travel distance. So one can indicate it as the over travel distance. So this AP and OR is given as the 8 mm. So let us indicate as AP1 is equal to 8 mm and OR1 that is equal to 8 mm. So from here we can see the overall distance traveled by the drill tool, that is the, let us indicate as LO. So overall distance traveled is L plus approach 1 plus over travel 1. So overall distance traveled is what? That is 50 plus 8 plus 8. That means 66 mm. That is the distance traveled by the tool during machining operation. So that we have obtained by using this basic criteria. Now another thing that we need to find, that is the revolution per minute, that is N. So we know the equation for that. Velocity, that is equal to pi dn divided by 60 into 1000. Now we know that V, that is the 0.5, pi is the constant, diameter, that is the 25, and we need to find divided by 60 into 1000. So after solving this equation, one will get the value of N as 191.08 revolution per minute. So when you solve this equation, you will get the value of N as 191.08 RPM. So now we have the value of L that we have got over here. We have the value of N also, and we have the value of feed also. So just by using this value in the equation of drilling time calculation, we will find the time required to drill a hole. So now time required to drill a hole, that is L divided by Fn. Now we got the value of L as 66 mm. Now the feed that is given is 0.5 mm per revolution, and the RPM we got, that is 191.08 revolution per minute. So if you find the unit, you will come to know that these 2 mm gets cancelled out, revolution gets cancelled out. So finally the answer that we are getting, that is the 0.69 minute. So this is our final answer. That means to drill the hole having the depth 50 mm and the diameter 25 mm, this can be machined in the time that is the 0.69 minute. And one can easily get the value for these also for the in the form of second also by just multiplying this value by 60. So I hope you get the clarity how to solve this particular equation and how to find the time required to drill a, right? So in this particular lecture we have studied about the main two important criteria. The first one, that is the time required to calculate or the time required to drill a hole using the equation L divided by Fn, and we have also understood the basic details regarding the work holding devices for the drilling tool. So looking forward to see you all in our next lecture. Up to then, thank you.